Well, we're about to start, and for those that have come here today to watch our seminar, please note the exits in case we need to leave the room on a short notice. Those that are on the internet, we especially encourage you to send in your questions at first opportunity so we could have time to take it during the Q&A. So with that, Pat?
Thanks, Peter. It's my pleasure today to introduce our three speakers for today's seminar. Our first speaker is Suzanne Paulson. She is a professor in the Department of Atmospheric and Oceanic Sciences at UCLA and the director of the UCLA Center for Clean Air. Her current research includes investigating the contribution of buildings and other features of the built environment on spatial distributions in complex urban environments, and the focus on today's seminar, linking the chemical composition of particles with their ability to produce reactive oxygen species when inhaled. In addition to her academic work, she's been a member of ARB's Research Screening Committee for a number of years now. Our second speaker is Dr. Cort Anastasio. He is a professor and vice chair of the Department of Land, Air, and Water Resources at UC Davis. His research focuses on oxidant generation by particles, as well as chemistry and photochemistry in cloud and fog drops, aerosol particles, and snow. In addition, his group has developed techniques to quantify the contribution of individual metals and quinones for reactive oxygen species formation from particles, and he will discuss this work in particular in today's seminar. In addition to his academic work, Cort is a member of the Scientific Review Panel on Toxic Air Contaminants for the state of California. And our last speaker is Dr. Alam Hassan. He is a professor and chair of the Department of Chemistry at Cal State University, Fresno. His research includes field measurements, mechanistic studies, and theoretical calculations aimed at improving our understanding of air pollution and climate change. In addition, his research group has been involved in the measurements of quinones and reactive oxygen species in ambient particulate matter for a number of years, and he will discuss this aspect of his work in today's seminar. So without further ado, Suzanne.
Thank you, Pat, and I guess thank you from all of us for that introduction. By way of outline, after a very brief introduction and a brief description of the field campaigns, Cort is going to talk about laboratory results that were part of the study, and then after that, Alam will discuss the quinone results from the field studies, and then we will see Cort again, and he will talk about DTT results from analyses that were performed on the field samples. And then finally, I will talk about OH and hydrogen peroxide measurements and also comparisons of those two reactive oxygen species with DTT results and provide some conclusions and acknowledgements. So to bring everybody on the same page, probably most people know what reactive oxygen species are, but the slides defines them. Superoxide, basically all of the things in red are reactive oxygen species. And that includes superoxide, O2 minus, hydrogen peroxide, and OH. There are a number of other reactive oxygen species, and some of them actually may have some activity in our assays, but we are mostly focused on these species. So reactive oxygen species are thought to underlie inflammation, and inflammation is in turn thought to underlie a wide range of adverse health outcomes. Reactive oxygen species can be divided into a few subcategories. So it turns out that the body creates reactive oxygen species as a result of a physiological response to particles and pathogens and other situations. This is one of the ways in which the body tries to defend itself. However, sometimes the levels of ROS get out of control and that results in inflammation, but also external sources of ROS can come into play and there's certainly questions about the balance of these two processes. So the physiologically produced ROS are endogenous ROS. The exogenous ROS are pretty much the focus of the study that we're going to talk about today. And one can divide those into those that are present in particles when they are inhaled. And those would include things like hydrogen peroxide, which is probably at fairly low concentrations, and organic peroxide, hydroperoxides, and so on. And then the ones that are generated once the particles are inhaled and come into contact with physiological fluids, which are also really more the focus of our assays. And then I also would like to note that there appears to be some significant overlap in the chemical components in particles that cause both exogenous and endogenous ROS formation. Okay, so a tiny bit about the field campaigns. We performed 2 field campaigns, one in Fresno in the wintertime, and Fresno has, in the winter, has a significant amount of residential wood burning influence as well as urban sources and some agricultural sources. And the other study was performed in Claremont in the Los Angeles Air Basin at a what we might consider a receptor site. And that has a lot of primary urban aerosol, but also because it was in the summertime and at a receptor site, significant amount of photochemical secondary organic aerosol. Samples were collected on filters, on 47 millimeters by my group and on high-vol filters by Alam's group. And they were collected 3 times a day, so for a 6-hour period in the morning, 6-hour period in the afternoon, and then 1 overnight sample which lasted for 12 hours. So as a result, the overnight samples typically had around double the mass of the other samples. This shows where in California these sites are. Fresno, of course, is in the Central Valley, and the Claremont site is fairly far inland. Downtown is sort of on the left edge of the lower map, but in the Los Angeles Air Basin. And both of the field sites were on top of university buildings, so fairly elevated from really direct surface sources. Very briefly, the assays that we performed were 3 ROS assays for production of OH, consumption of DTT, and actually the steady state concentration of hydrogen peroxide, and I'll talk a tiny bit more about those in a couple slides. We also performed a number of supporting measurements to try and understand the chemical components that were leading to ROS formation, and that includes measurements of quinones made by Alam's group, and soluble transition metals, mostly with inductively coupled plasma mass spectrometry, but we also performed a number of measurements, actually basically analyzed all of our samples for soluble iron 2 and iron 3 with an assay called ferrozine, and ferrozine is something that chelates available iron, so it turns out it produces, it measures much smaller quantities of iron. And I do want to point this out now, and most of the data that I will talk about is this iron measured with ferrozine, because that is so much more tightly correlated with ROS than iron measured with ICP. And the ICP measurement was also a soluble metal measurement, as it says, so it will also in turn be much lower than, for example, total iron when filters are digested. So we also estimated brown carbon on our filters. This is a 3-dimensional fluorescence spectrum of, you can't really see the wavelengths, but this is all in the near UV. A brown carbon for the Fresno filters and also mass. So most of these analyses were done on filters that had been frozen and stored. However, most of the OH measurements were made on site, and also the soluble iron measurements were made on site. We do know that the signal does decay. ROS activity does decay, and this is just a little bit of data kind of showing that when you store filters. So, okay, so a little bit more about the ROS assays. There are a lot of ways in the literature to measure ROS, and this is not all of them, but this is a fairly large fraction of them. We used the three that are in red. So we measured OH with terephthalate. Other investigators, including Court's group, actually uses benzoate, but we use terephthalate. We do these measurements and we use terephthalate. This basically just produces a molecule has a molecule that reacts with the OH that has very specific fluorescence. OH is the most reactive oxygen species, and it's responsible for lipid peroxidation, DNA damage, protein oxidation. It's clearly, large amounts of OH can do significant damage. We also measured hydrogen peroxide, and hydrogen peroxide is an intermediate in ROS chemistry. It potentially contributes to other, hydrogen peroxide itself is an ROS, but the other thing that I do want to point out here is that unlike the OH, which is cumulative amount of OH that has been created in the solution, and DTT, which is actually a consumption rate, hydrogen peroxide measurement is a measurement of the concentration at a particular time. So it's being formed and destroyed. So it's a fundamentally different measurement than the other measurements. DTT consumption, dithiothreitol, this molecule, mimics biological reductants and is oxidized by ROS generating PM components such as metals and quinones. And some of the other ones listed in black are other ones that are reasonably common in the literature but are not explored here. We mostly used one extraction solution which we refer to as simulated lung fluid, or SLF. And it consists of a solution at pH 3.4 with phosphate buffer with sodium chloride to try and mimic the ionic strength of physiological fluids. And it contains 3 lung antioxidants, ascorbate, glutathione, and urate. And it also contains citrate, which is in there to mimic the activity of proteins in terms of its ability to chelate metals. We also have a little bit of results that were performed in concentrated phosphate buffer. Actually, all of the DTT measurements were performed in concentrated phosphate buffer, and a little bit of results with lung lavage fluid and just water at pH 3.5. The extraction solution is really important in a number of ways, some of which will be discussed by Court, I think, but this shows the effect of, this was one example in which the extraction solution is important. This shows basically largely the effect of pH, but also the effect of other solutes in these solutions in terms of the amount of soluble iron. And this is iron measured with a ferrozene assay. So this seems to be the most active portion of the total iron. And we have the same samples extracted at pH 3.5 in SLF, in lavage fluid, and in phosphate buffer. And but I note that the lavage fluid is a different patient for each bar, so they're a little variable, probably because they are different patients and they have different components in them. But you see very dramatic differences in the amount of soluble iron, especially in the Claremont samples, less so in the Fresno samples, and we think that may be because of the sort of activation solubilization by the biomass burning HULIS that is in the Fresno samples. This shows similar thing for copper, but just for pH 3.5 and SLF. And in this case, the copper actually is not so sensitive to the extraction solution. It's much more similar, probably more soluble. And with that, I will hand it over to Court.
All right, thank you. I'm going to talk first about the laboratory work we did looking at OH, hydroxyl radical, and hydrogen peroxide formation. And I just want to acknowledge first that this is work from Jessie Charrier, who's an ARB employee, and she's done all the lab work and all the DTT stuff that I'm going to talk about today. All right. Okay, so the last parenthetical phrase of the title was something about the effect of physiologically relevant solutes, and that's what I'm going to talk about on this slide. So we were interested in how different antioxidants in the surrogate lung fluid impact the ability of different metals and quinones to produce hydrogen peroxide. We had done previous work looking at OH generation with the same idea, and we found there were big impacts, and so we went to look to see what happens with hydrogen peroxide. So we're going to look at how ascorbate, citrate, glutathione, and uric acid affect things. And you can see in this first graph, which is for 250 nanomolar of copper, that the composition of the SLF has a big impact on how much ROS you make from a given redox active species. So we found that you need ascorbate in these solutions to make, in this case, hydrogen peroxide. So ascorbate's the source of electrons that the metal or the quinone can then shuttle onto dissolved oxygen to make ROS. And so you can see here with ascorbate, you get the big signal. If you have just citrate, nothing happens. Glutathione, you get a small amount of signal. And then when you start having mixtures, you get sometimes enhancements, sometimes suppression. So in the full SLF, which is the condition here, you can see that copper is much less reactive at making hydrogen peroxide than it is in the presence just of ascorbate. Now, we understand that, we think, because as you add different species into the SLF, you can change the speciation of the metal. For example, from copper ascorbate, copper citrate, copper glutathione complexes, and those have different reactivities. What we didn't expect is when we look at quinones, you also see an impact. So for quinones, ascorbate is also the reductant, it's the source of the electrons, but when you add all four SLF components, the antioxidants, you see a suppression in the ability of quinones to make hydrogen peroxide, which is surprising because it's not affecting the speciation of the quinones. The bottom line is the composition of your extraction fluid has a significant impact on what you measure in terms of ROS production. And so this 4 antioxidant mixture in the SLF is the most complicated redox active realistic solution. It's obviously not lung fluid, which is extremely complex, but we think at least with these 4 antioxidants, you do a decent job of mimicking the redox environment of lung fluid. And so that's what we're going to use now for all the subsequent measurements. Okay, we are interested in which species in particles can generate different ROS, and so part of that, in order to understand that question, you have to understand how well do individual redox active species generate a given ROS. And so what I'm going to look at in this slide is hydrogen peroxide. So you can see in this top graph, we call these concentration response curves. We measure, in this case, the formation rate of hydrogen peroxide as a function of the concentration of the redox active species. So you can see we've got copper in purple, which is a curved line, and then 3 different quinones, 1,2-naphthquinone, phenanthrene quinone, and 1,4-naphthquinone. And so at a given concentration, we can determine what the rate of hydrogen peroxide formation is. We tested 10 transition metals in total. Out of the 10, only copper could make hydrogen peroxide. We also looked at mixtures. So here's some examples of the data. So the colored bars in any case are how much, well, in this case, the rate of hydrogen peroxide production from that individual component. So in this case, this is a solution of 500 nanomolar copper, 500 nanomolar PQN, and these are the individual responses, and if we assume it's additive, this is what you would expect. And then when we do the mixture, you can see we get essentially the same thing. So for hydrogen peroxide production from quinones and copper, it looks like the results are additive. When you add iron, you change things. Now there's a well-known Fenton chemistry where iron 2 reduces hydrogen peroxide to form OH. So we know that iron suppresses hydrogen peroxide. And we see that in the mixture measurements. So here's naphthquinone with iron. This is what naphthquinone should be making, and this is what it makes in the presence of iron. And so you can see this suppression of hydrogen peroxide from the naphthquinone, from the copper, or from the mixture of the quinone and the copper. So iron suppresses hydrogen peroxide. In the laboratory, Jesse did on the order of 30 different mixtures, so we could come up with essentially a laboratory model for the impact of iron on hydrogen peroxide. When we apply that model, though, to ambient PM extracts, it doesn't work. And that's what the final graph shows here. So the y-axis is the expected rate of hydrogen peroxide from our lab-based model, and then the x-axis is the measured rate of hydrogen peroxide production from the PM extracts. And you can see there's no relationship. And so this is the one case we found for hydrogen peroxide that you can't use just the lab stuff to understand the PM extracts, because we think organics in the PM are altering the ability of iron probably to destroy hydrogen peroxide. Okay, and then the final goal we wanted to understand for hydrogen peroxide production was which species in particles are generating hydrogen peroxide. And I'm going to hold on to that thought for a few slides, and then I'll discuss it. We then moved on to OH and did the same thing, trying to understand how can individual metals and quinones make OH, how reactive are they, what happens in mixtures, and then which PM species are responsible. So these are the concentration response curves for OH. Again, we looked at the 10 different transition metals, and we found that copper, again, can make OH, and in this case, iron can also make OH. The other 8 transition metals we looked at that are listed there did not make any appreciable amount of OH. 3 of the 4 quinones also made hydroxyl radicals, you can see in the figure. So that's the 1,2-naphthoquinone, phenanthrene quinone, and then the 1,4-naphthoquinone. We then looked at mixtures. If you look at mixtures of copper and quinones, the results appear to be additive. So you can see that in the first set of bars here. So here's the individual responses added together, and this is what we measure in the mixture, so that's fairly close. When you start to add iron, though, to the mixtures, you find that you get this synergistic production of OH. So you get more OH than you would predict from the individual species. And you can see that in the next 4 sets of bars. So iron and copper. So here's the individual contribution from iron, the individual contribution from copper if it was additive, and then the gray bar shows the mixture. So you can see you're getting this additional OH production beyond what you'd expect from the 2 individually. And the same thing happens for iron and the phenanthrene quinone, iron, copper, and quinone, and these iron, copper, quinone mixtures. So there's this synergy that can enhance the OH production by up to about a factor of 2. Now in this case, we find that when we take the laboratory model of this iron synergy and we apply it to ambient PM extracts, it actually predicts the OH production quite well. So in contrast to the hydrogen peroxide as an endpoint for OH, we see good agreement between the lab results and the ambient PM results. And then I'm going to show the importance of individual species for OH in just a slide or 2 slides. All right, so before I can get to, really for me, the fundamental question, what species in the PM are making ROS? I want to explain our approach. So we call our approach the mechanistic approach. To contrast it with what's been done in the past. In the past, the tool people have used to try to understand which PM components are linked to ROS formation, people have always looked at regressions. And this has been going on for over a decade now. So you look at linear regressions between your ROS output and PM components, and if they're regressed, if there's a good correlation, you say that thing is probably associated with ROS production. But there's no mechanistic basis for that, right? And especially in particles where you've got a lot of things that are correlated with each other, a correlation doesn't necessarily mean a mechanism. It doesn't mean that it actually is happening. The other problem is, if you look at the second bullet point there are a number of species that have non-linear concentration response curves, as I just showed. So copper and manganese are the 2 big examples. So you wouldn't expect necessarily that a linear regression would tease out their relationship. So the mechanistic approach, we developed it in roughly 2008. We've used it in about 7 studies since then. That includes DTT, hydrogen peroxide, and OH studies. And the way it works, well, sorry, take a step back. But the advantage of the mechanistic approach is you're actually taking into account the reactivity of the individual redox active species and the amounts that are present in a given particle extract. So it's almost a chemical mass balance approach to ROS. And what we do is we start with the concentration response curves, which I've showed you in the past slides for hydrogen peroxide and OH. This slide is showing the concentration response curves for DTT. So as a function of individual redox active species concentration, the rate of DTT loss from that individual component. So we do that first in the laboratory. Then we take ambient PM samples, measure their concentrations of transition metals, and if alum's with us, quinones. And so this is an example from a study that we did with Tony Wexler, the Fresno SOTOX samples. So we've got here 10 different samples, 2 different sizes, ultrafine, submicron fine. And you can see the metal concentrations for each sample. So purple is copper, blue here is manganese. So we'll measure for each sample the composition. And then we take the composition of an individual particle sample, and we essentially multiply it by the concentration response curve to determine what rate, in this case of DTT loss, would you expect in that sample from that specific component. And when we do that, we can apportion the total reactivity of a sample to its individual components. And so that's what this bottom graph is showing. This again is from the SOTOX work. So these same different samples, you can see, there we go. The gray bar is the measured value for that sample. And then the colored stacked bar are the contributions, in this case, from copper at the bottom and then manganese. And so in this particular sample, for example, you can see the copper explains roughly half the reactivity, manganese maybe a quarter, and then we're missing about a quarter. So species that we haven't identified are also significant. So we can do that on a per sample basis. All right. Now there are uncertainties with this approach. One of them is how do particle components impact the reactivity of individual metals? Again, for hydrogen peroxide, we know this approach doesn't work particularly well, but we think for DTT and OH that it's quite robust. The other part is the mixtures. We've done a fair amount of work on mixtures, but there's always more work that one could do. Okay, so now I'm going to apply this mechanistic approach to a hypothetical PM sample. The question again is which PM components are responsible for the generation of ROS. So we're going to take the median of average values from I think 8 different studies across the US to come up with a hypothetical PM sample. And we're just interested in the redox components. So we don't care about ammonium nitrate or sulfate, any of that. We're going to look at the metals and the quinones. So when you do this, you get water-soluble metal concentrations that are quite low, 7 nanograms per cubic meter of air for iron, and then 2 for copper and manganese, and then the quinone concentrations are quite a bit less. We then take this hypothetical sample, we can calculate from our concentration response curves what the ROS production rate or the DTT loss rate should be for the sample, and then we can apportion that reactivity to the individual components. And what we find is that copper rules. The first pie chart here is for DTT. Roughly half of the DTT loss for this hypothetical sample is due to copper, about a quarter from manganese, and about 20% from phenanthrene quinone. Next is hydrogen peroxide. Again, hydrogen peroxide is uncertain, but if we assess the impact of organics as just affecting the ability of iron to destroy hydrogen peroxide, then we come up with almost all hydrogen peroxide is from copper. And then finally, OH. OH is a little more complicated. Copper is important, about a third. Iron's about a quarter. And then this bottom stripy part, this is the synergy that I talked about. So iron-copper synergy here is responsible for about a third. So it roughly doubles the reactivity of the copper. So copper is a big player based on this in ROS generation from ambient PM. If you look at the California reference exposure level, it's 100 micrograms per cubic meter. I'm going to go out on a limb and say that's likely not health protective. Right? It's an enormous value. So we've been talking with Ralph and with people at OEHA, and they're currently reassessing the copper rel. So I'll be very interested to see what comes out of that. It's not really that surprising in hindsight that copper appears to be driving a lot of the ROS production, because if you look at the literature, there's a lot of in vitro, in vivo, and even now epidemiological studies that very clearly show copper is highly redox active and toxic. All right, with that, turn it over to Alan.
Good afternoon. So I'm going to talk a little bit about quinones. And so as we've already heard, had a nice introduction into why they're potentially important. My own interest in quinones goes back a long time. It makes me feel old looking at this slide, realizing how long I've been doing this. But back in 2004, 2005, we did our first measurements of quinone levels in Fresno. And taking periodic measurements over the course of a year, we found that the levels were actually fairly high compared to what we could find in the literature at the time. We also did some work with a variant of a DTT assay, where we looked at the production of hydrogen peroxide in the presence of DTT from organic extracts. So these are different from the measurements that Court did because they don't contain the metals. It's just the organic soluble fraction. But in that work, we found that we could essentially account for all of the hydrogen peroxide production by those extracts. And it was really dominated by phenanthroquinone, with a small contribution from the 1,2 and the 1,4 naphthoquinone. So in terms of our contribution to the project, the primary goal was really to quantify the levels of the quinones to allow the other groups to be able to assess the relative importance of those compounds in generating ROS. But obviously, if it turns out that quinones are important, we want to make sure that we can also get some insight into where those quinones are coming from. We've also had a nice overview into the study. So Suzanne already talked about the sampling sites in Southern California and Central California. So in Claremont, the measurements were done in the summer of 2012. And as Suzanne talked about, that contains organics that are mostly anthropogenic. And because it's in the summer, there's a significant photochemical component to the organics that are present. In Fresno, it's more primary, and we get a lot of wood burning and biomass burning, so that tends to dominate what's in the samples. Procedure, we collect with a high-vol sampler for our PM 2.5 on 8 by 10 inch Teflon filters, and we had a puff sampler running alongside that to get some of the semi-volatiles. And the goal was to collect 3 measurements per day, a morning, afternoon, and an overnight sample. So we took the filter samples. We did an extraction with the SLF solution so that our organic measurements match what should be present in the measurements that the other groups are doing. But we also extract into an organic solvent to get the total quinones that we can get from the filter. And the puffs were extracted with organics as well, and we quantified by GCMS. And we also provided some sections of our filters to Davis and UCLA for some of their measurements. And we had some parallel measurements going along that leveraged the work that we were doing here. We did some in vivo measurements, in vitro, excuse me, not in vivo, and those are still ongoing, and we don't really have anything to talk about at this point, but those are taking place. This is a list of quinones that we looked for. The ones that we expected, I can't see where my cursor is, there it is, to see that were relevant, the phenanthroquinone and the 1,2 and the 1,4 naphthoquinone, which we've already heard about this afternoon. And just kind of a bird's eye view of a comparison of the results that we got from the 2 sites. So the figure at the top here is showing the average mass loadings of the individual quinones that we saw at the 2 sites over the course of the set of measurements. So we see a wider range of quinones at the Claremont site, but the average mass loadings are significantly lower than the measurements that we get at Fresno. So in Fresno, we see primarily anthraquinone, 1,4 naphthoquinone and phenanthroquinone, and there's a significant difference in the mass loadings of those compared to the corresponding chemicals that we saw at the Claremont site. In terms of a diurnal variation, we see the similar pattern for Fresno and Claremont, an increase from morning to afternoon and then a drop overnight, although none of those differences are statistically significant. I think the p-value for the afternoon versus overnight is about 0.07, 0.08. This is a reminder to myself to make sure that I'm careful when I talk about the concentration of the quinone, because we have 3 different measurements going on. We have the SLF measurement, which is the value relevant to understanding the contribution in the assays. But these compounds are sparingly soluble in water, so there's a significant fraction in all 3 that only comes out when we add the organic extraction solution as well. Plus, these things have high enough vapor pressures that there's some of them in the gas phase as well, especially for the 2-ring compounds where, in fact, most of it's in the gas phase. These are measurements from the Fresno site. So just a quick look at the measurements from Claremont, the 56 samples that we got from there. As you can see from this, there's quite a lot of inter and intraday variability. And so, again, when we look at the diurnal variation, there's a pattern, although it's not statistically significant. So we went on and we did some back trajectory analysis to try and provide a little bit more insight into what's going on. So in these visualizations, what we've done is we've run 12-hour back trajectory calculations with high split, starting every 1 hour over the course of the sampling period. So we tag each of those back trajectories with the mass loading of the chemical that we measured in that particular sample, plot it on a 20 by 20 grid, and then we average the concentration corresponding to each trajectory passing through a particular grid square to get the z-value for the plot here, the color that we have here. So just to try and give you a sense of what we have for this bottom right graph, which shows all of the measurements that we did, when we see a region that's red, what that's meaning is that all of the trajectories that pass through that particular geographical area correspond to high measurements of that compound when it gets to the sampling site, which in this case is, keep losing my cursor here, is right there. So the overall behavior that we see is the bottom right graph, and so you can see that there's a red patch that lies to the southwest of the sampling sites. It borders onto Long Beach down towards Irvine. When we look and separate out the trajectories by the time of day, night versus afternoon versus morning, then what we see is that the trajectories that come from that particular direction, we tend to see the highest concentrations in the afternoon. So we could rationalize this either as the emissions occurring in the morning, and so they arrive at the sampling site in the afternoon, or it could be photochemistry, which seems to be the most likely explanation. So emissions in the morning, photochemical transformation into quinones during transport to the Claremont site, and that's why we see what we see. Doing the same kind of analysis for Fresno, again, these are all of the samples that we analyzed in that period. Again, we see the diurnal variation morning to afternoon to evening. And we also did a comparison of the measurements from the 2013 campaign to the winter measurements that we got back in 2004, 2005. So for phenanthroquinone, anthraquinone, and 1,4-naphthoquinone, there's no difference in the levels between those two periods. The total quinones were higher in 2004, 2005, and it's mostly the other compounds that weren't measured in the most recent campaign in Fresno that were responsible for that. Again, we did the back trajectory analysis. The scale here has changed, so now it's normalized to mass rather than to volume, and we're just looking at phenanthroquinone. But again, we see a strong directionality to the mass loadings that we measure at the Fresno site, which now is down here. So when the trajectories are coming from the Bay Area, then we tend to see this red patch indicating that those trajectories are correlated with high concentrations of phenanthroquinone. Separating it out by time of day, we see also that there's a variation between our morning versus afternoon versus nighttime samples. So for the nighttime samples, it seems like those high levels of phenanthroquinone have gone away. And there's a statistically significant difference between the morning and afternoon measurements and the nighttime measurements specifically for phenanthroquinone. So just to summarize some of the key points from this, the mass loadings of quinones are higher in Fresno, but we see more quinones in Claremont. Both site measurements are consistent with some photochemical production of the quinones and from urban sources. And so in Fresno, on that last slide, I showed you that there's no change in the redox active quinones, the 1,4-naphthoquinone and the phenanthroquinone, but the total quinone mass loadings in Central California have decreased. So now I'll turn it back over to Court.
Like an alum sandwich, right? Okay, so now I'm going to talk about DTT work on the field samples that Suzanne and Alan collected. But first I want to talk about something that Jesse discovered while we were doing this work, and this is a mass bias in the DTT assay. This is something specific for the assay. It's not something that's specific to us. Normally in the DTT results, you normalize your rate of DTT loss by the PM mass concentration in the extract solution. So that's called the mass normalized rate. When you do that, you're implicitly assuming that the response is linearly related to the mass in the extract, which we found is not true. And we know that's not true for copper and manganese from the concentration response curves. So what Jesse did was first look at hypothetical PM sample and see how the DTT response would vary as a function of PM mass in the extract. And that's what you see on the top here. So again, this is a hypothetical sample with some typical amounts of copper, manganese, phenanthroquinone, and cobalt. You can see on the bottom, so we've got PM mass concentration of the extract on the x-axis, and you can see for cobalt and phenanthrene and quinones, both have linear responses. But remember, you may remember, that manganese and copper have nonlinear responses in the assay. So if you think about this individual PM sample as a function of PM mass extract, what you would get is this dashed line. So as you increase the mass concentration, the DTT response increases, but not linearly. When you then take that data and mass normalize it, this is what you get. So the y-axis is the mass normalized DTT response as a function of PM mass concentration, again for a single PM sample. Now notice for PQN, phenanthrene, quinone, and cobalt, that they're flat lines. That's the implicit assumption in the assay. But that's not true for copper and manganese because they don't have linear concentration response curves. So what you end up with in the sample itself would be something like this dashed line, where if you're using low PM mass concentrations, you're going to get a very high mass normalized response. And if you use a high PM mass concentration, you're going to get a lower response. And over the course of this PM mass concentration, it varies by about a factor of 10. So it's a big deal. It's not a small effect. So we then looked at this for the Claremont and Fresno samples. We looked at 5 Claremont samples, 3 Fresno samples. And what we see is what we predicted from the hypothetical sample. So each colored dot represents a different sample, and you can see as you increase the mass concentration of your PM in the extract, the DTT mass normalized rate goes down. That's a big problem because it means you can't compare DTT results for samples that were studied at different masses. And every sample is studied at a different mass, both within a given study as well as between studies. So you have to normalize DTT results to a constant PM mass concentration. And we have a paper coming out in Atmospheric Environment where we recommend doing this for a PM mass concentration of 10 micrograms per mil. Okay, so that's the background. And we then took this idea and we're going to normalize all the DTT results that I showed you to this recommended PM mass concentration. Okay, just very briefly, metals and quinones at Claremont and Fresno. The metal story is essentially most of the transition metals at Claremont and Fresno are very similar to what's been shown in the past. The copper is fairly high. It's not as high as it's been reported previously in LA, but it's higher than in more rural or suburban sites. And then quinones, Alan just talked about the quinones that we find, or that Alan found at Fresno and Claremont, are within the range that people have reported in the past. These are the DTT results. I'm just showing them for Fresno. The Claremont results are very boring. It's essentially the same number, bouncing up and down a little bit. Fresno, some things actually happen. So if you look, the red is the PM mass concentration. That's on the right y-axis. And you can see there are some large variations. There's a period here that I believe was rain, where the PM concentrations go quite small, below 5 micrograms per cubic meter, and then they recover. The blue line shows that the DTT response, mass normalized, and you can see it's in the beginning fairly constant. Then when you get very low PM masses, the mass normalized DTT response increases, suggesting perhaps you're getting rid of some non-DTT active PM mass. And then it remains elevated for the rest of the campaign. We don't see any difference in the averages between morning, afternoon, and overnight samples. And if you look at the literature, the rates that we see here in Fresno are similar to the quite wide range that's been reported previously. One of the things that's interesting is this impact of mass normalization and the DTT mass bias. So we took the Fresno results, and as I mentioned, we normalized them to this constant PM mass extract, 10 micrograms per cubic meter. But this table compares what would happen if you didn't do the normalization. So the middle column here, which says standard mass normalization, sorry, my cursor, there it is. Standard mass normalization, this is if you didn't normalize your PM extract. And you can see that the range is from roughly 20 to 200 picomole per minute per microgram. If you do the normalization that I just discussed, you can see that range tightens up quite a bit. It goes from 55 to 150. The mean does not change very much. It goes from about 80 to 90. But that's probably because our mean PM mass in the extract was around 10 micrograms per cubic meter. But the thing that really does change is the variance, the standard deviation or the relative standard deviation. So you can see if you look at the RSD, if you don't normalize the PM extract mass, you've got an RSD of 50%. If you do the normalization, it's approximately half that. So what that means for this particular study is if we didn't do the PM mass normalization, about half the variability in the response we see for DTT would simply be an artifact of the DTT assay. So this is really important for field studies that use DTT. You have to do this mass normalization. Okay, I mentioned before we're very interested in what components are responsible for ROS generation, in this case DTT loss, and so we're going to use this mechanistic approach that I mentioned. When we do that for Claremont, which is on the top, and then Fresno on the bottom, you can see it's a sea of purple, right? And purple again is copper. So we find that copper is dominating the DTT loss in both Claremont and Fresno. There are some important contributions from quinones. You can see in this period here in Fresno, this was the rain period where the PM mass goes quite low. You can see large contributions from phenanthrene quinone, the yellowish color, and then the gray are the unknown. The unknown components are also definitely significant. If I average across each site, that's what's shown in this graph. So this is the average percent contribution to DTT loss for each redox active species. So Claremont's in blue, Fresno's in red, and you can see the copper is dominating as we just saw. So roughly 80% of the response on average at Claremont is because of copper, and about 70% at Fresno is because of copper. Next most important generally is the unknown component. So it's roughly 10 to 15%. Phenanthrene quinone is important in Fresno. And then manganese is small but significant at both sites, 5 to 10% of the total response. Suzanne's going to talk quite a bit about regressions in the last component of the talk. So I just want to try to discuss the mechanistic approach versus the regression approach. As she'll discuss, there are strong correlations between the DTT rates and iron, copper, and manganese at Claremont. And then at Fresno, HULIS is very important. And then iron and copper. I mean, our results for the mechanistic approach clearly show that copper is dominating the system. The unknown, I think based on the HULIS regression that Suzanne's going to show you, it's likely that a significant component of the unknown at Fresno is probably HULIS, or biomass burning aerosol. She's also finding that iron is important in the correlations, but iron is very, very weakly active in the DTT assay. And so using the mechanistic approach, we come up with that iron is responsible for less than 1% of the total DTT loss at either site. So I think this is the case where the iron is not actually what's responsible for the DTT loss, but maybe it's either correlated with another component, which must be copper, or it's a correlation that doesn't mean causation. It is possible that there are organics in the sample that are changed in the DTT reactivity of the different species, but we haven't found any evidence for that in our past work. It seems like the lab solutions match very nicely with the ambient PM. So that is the end of my component, and we're going to turn it over to Suzanne for the home stretch.
Thanks, Court. So yes, back to regressions. I guess that the one thing I will say about regressions is that I think that the mechanistic approach is incredibly valuable. But one would expect that if copper is responsible for a huge amount of the activity, then that would show up in the regression. So they should hopefully come together. But I did want to show before I did anything else the potential. We looked at recognizing the sort of mass in the solution effect that Jesse and Court found, which makes an enormous difference to the DTT assay. We looked at that for OH and hydrogen peroxide, and this is just OH and hydrogen peroxide normalized to the amount of PM mass versus the PM mass. So in this space, you would expect to see an effect. And for the most part, you don't see, well, certainly at very low concentrations, in some cases, you do see a little bit of an effect. How do I get the, there? But at most concentrations, you don't see much of an effect. And clearly it's at very small compared to the effect that is observed for DTT. So our results are not corrected in the way that the DTT assays were corrected for the nonlinearity of the copper and the manganese in solutions. Okay, so ROS assays in relation to one another. So this shows OH versus DTT, and in general they're pretty well correlated, especially for Claremont. However, the DTT response relative to the amount of PM was almost the same for the two sites, but the OH was pretty different. So most of the difference in those two, and the slopes of those two lines, is the result of differences in OH production at the two sites instead of DTT production. So this shows hydrogen peroxide relative to OH and DTT. So hydrogen peroxide is, we get much more scattered results. Basically, no matter how we look at it, the lab results had much more scattered results. The field results are much more scattered. We clearly don't see nice linear relationships, and we see the different samples. So the red is the overnight samples, the sort of dark bluish purple is the afternoon, and the lighter blue is the morning. We see the samples kind of segregating kind of by time of day. And the other thing I should point out is that the top two plots are Claremont, and if you look at the x-axis, almost all of my slides have the same axes, so that they're all directly comparable, but the hydrogen peroxide production in the Fresno samples was a factor of 10 higher than it was in the Claremont samples. So there's vastly more hydrogen peroxide production, at least for some of the samples, particularly the overnight samples, which are the ones that contain the most biomass burning aerosol, for Fresno compared to Claremont. So another question that I would like to cover is, do chemical components do a better job than mass at predicting ROS? So clearly mass doesn't produce ROS, but we regulate mass. Chemical components do the reactions that produce reactive oxygen species. But in the case of DTT, actually mass does quite a good job of predicting ROS or DTT consumption in those assays. And in fact, for Claremont and Fresno, the slopes are basically the same. Correlation coefficients are pretty consistent with each other as well, and combined together, they have a very, very strong correlation with mass. They are, however, better predicted, especially in the case of Claremont, by chemical components in the particles. However, in the multivariate regression, iron does come out as being quite significant in the DTT assays, even after the DTT has been corrected for the mass in the solution. For Fresno, we didn't really do multivariate regressions because we have some data gaps and we don't really have enough data to do reliable multivariate regressions. But biomass burning hue list is basically as good of a predictor as mass in the Fresno samples for the DTT consumption assay. For OH is also strongly correlated with mass, but somewhat less so than DTT. And the slopes, as I pointed out before, are quite different between the two sites. There's more OH produced per mass in Claremont than there was in Fresno. And actually, if you look carefully at the Fresno data, the green squares with yellow, orange rims around them show the afternoon samples in Fresno. Those had very little OH activity and almost no dependence on mass. Basically, the sort of slope of that line is all driven by overnight samples and to a lesser degree morning samples, which have significant amounts of biomass burning aerosols. So the afternoon samples in Fresno are at least in the OAH assay, quite inactive compared to the other urban samples. This shows OH just for Claremont, and Claremont OH is quite well predicted again by iron, and this is iron measured with a ferrozine assay, not any of the other, so it's sort of a subset of the soluble iron in the samples. And those iron, copper, and manganese together do a better job of predicting OH formation than mass by a fairly significant amount. For Fresno, again, we see that biomass burning humus is the most predictive individual chemical component that we measured, and but in this case, mass does a significantly better job. Hydrogen peroxide, again, the data is quite scattered. A combination of manganese, copper, and iron does do a better job than mass, but it's still not doing a very good job. So that's for Claremont. For Fresno, we see a terrible correlation between hydrogen peroxide and mass. Mass is quite tightly correlated with biomass burning humus. That's in the upper right corner, and you can see the red triangles, which are the overnight samples, and the open diamonds, the morning samples, have pretty sort of similar amounts of biomass burning humus per mass of particles, but the afternoon samples have significantly less. Those are the sort of purple-blue squares. Hydrogen peroxide is pretty well correlated with biomass burning, at least compared to other predictors in the Fresno samples. I wanted to show you the soluble metal data as well for the different sites. This is copper, and copper is pretty similar, a little bit higher in Claremont, not terribly well correlated with mass. And if you look at the copper, you do see some kind of noticeable things. For example, the afternoon samples in Claremont had very low soluble copper. Those are the purple triangles. And we saw a kind of similar thing, but less dramatic in the Fresno afternoon samples. For some reason, rather low levels of copper. Soluble iron shows interesting patterns. It's overall higher in Fresno, but all of the high samples are samples that have significant amounts of biomass burning humus, and the ones that don't have significant amounts of biomass burning humus, particularly the afternoon samples, have very low iron, at least iron that is available to the ferrozine assay. Iron is quite well correlated with mass, however, for Claremont, but not Fresno so much. Manganese is more different between the two sites than copper and at least most of the iron data. There's significantly more manganese in Claremont than in Fresno, and while the data are fairly scattered, especially in Fresno, there's no particular sort of dramatically lower metal content in the afternoon samples for manganese. So, so a little bit more about biomass burning humus interactions with iron and copper. So these are this is a result of a kinetic study that one of my students and I recently submitted, looking at the effect of not biomass burning humus, unfortunately, because it was difficult to get enough of that material to really do the study on, but instead something that is believed to be similar, certainly not identical though, folic acid that has been recovered from river organic material. But what it shows you is the first line of each of the pairs of reactions is the rate of the reaction with just the iron atom, so iron 2 plus O2, for example, making iron 3 plus superoxide. If we add in fulvic acid, it interacts with the iron 2 and it enhances the rate constant by something like a factor of 3. Fulvic acid seems to have a very strong influence on all of the rate constants, except at least in our study, we did not have evidence for it having a significant effect on the reaction of iron 3 recycling with ascorbate, which is in our SLF solutions. But you can see that the really dramatic impact of organic chelators on the activity of iron. This shows a slightly different segment of our data. This is hydrogen peroxide, but this has been sitting around in solution for longer than the other data that I've shown you. The other data were, our data were extracted for 2 hours. I think Court's and Jesse's were 1 hour or 4 hours. Well, some of them are initial rates anyway. But anyway, they're much shorter than 24 hours. But I picked the 24-hour data because the effects are a little bit more dramatic, and also the extraction solution has reached a little bit more of a steady state. And what you see here are Claremont on the left and Fresno on the right, and the relationship between hydrogen peroxide and iron measured with the ferrozene assay and copper. And you see, first of all, you see very different patterns between Claremont and Fresno. So clearly the presence of biomass burning humus is having a significant impact. You see in, so the copper clearly in these assays in the Fresno samples seems to be more sort of, it falls on more of a line than the iron does. The iron is kind of spread out all over the place, so there seems to be indications of significant interactions between copper and the biomass burning humus in the hydrogen peroxide data. So there's something in the solution that is making the hydrogen peroxide more stable and or formed at higher rates, and there are several possibilities for that. This data seems to imply that while iron almost certainly has a significant role to play in this, copper does as well. And this slide shows hydrogen peroxide. It shows actually the same data on the right that was on the last slide, but hydrogen peroxide and biomass burning humus. And when we plot hydrogen peroxide versus biomass burning aerosol content, we see the data are kind of in different sets. The afternoon samples seem to be influenced, are actually consuming hydrogen peroxide and seem to be influenced by the iron in those samples, and the iron that is not interacting with humus because there's not a lot of humus there. The other samples with a lot more biomass burning humus are producing and or stabilizing hydrogen peroxide, inhibiting the destruction of hydrogen peroxide, and this behavior seems to be more related to the copper in those samples. Okay, so by way of summary, DTT is pretty much the same at the two sites once aerosol mass is considered. OH is higher in the Claremont samples and very low in the Fresno samples unless they contain biomass burning aerosols. Hydrogen peroxide is much higher in the Fresno samples where there's significant biomass burning aerosol present, and this seems to be associated with strong interactions between biomass burning aerosol, iron, and copper, which can have very substantial influence on the rates of some of those key ROS forming reactions. The largest differences between Fresno and Claremont are significant biomass burning aerosol in the Fresno aerosol, which is absent in the Claremont aerosols. Somewhat higher copper, iron, and manganese in Claremont compared to Fresno, except in samples with high biomass burning aerosol, which had high sort of bioavailable iron. The biomass burning aerosol activity can be actually due to several things going on. One of them is higher solubilization of available iron. Probably the copper solubility the copper already seems to be fairly soluble, so potentially not so much a solubility effect for copper. Higher iron content, and increases in the rates and changes in the relative rates of the oxidant producing reactions when iron and copper are complexed by biomass burning aerosols. So this is a comparison of the field results and the lab results. As Court indicated quite forcefully, copper is kind of the number one actor in the lab results in all cases. In the field results, we were not really able to reproduce that in all cases, although certainly there seems to be a significant role for copper. Soluble iron measured with the ferrozene assay came out ahead in a number of cases. And where there's biomass burning HULIS, it was also very, very important. This obviously wasn't tested in the lab. Mass did a pretty good job, especially for DTT, but chemical components were better. So I don't have time to put this in a lot of literature context, but I did want to point out a recent study that did a very extensive field study that measured DTT consumption and also ascorbic acid consumption. And as Court pointed out, correcting for the mass in the assay is important. This was not done for this data. I will note that when Jesse and Court did it for their data, it didn't sort of qualitatively change the result. It certainly made the results look much, much better, but it didn't qualitatively change the results. So with that in mind, this group found very strong relations between DTT and iron, and water-soluble organic carbon and biomass burning aerosol, which is actually quite consistent with our field results. And for ascorbic acid, they found very strong correlations with copper. So the DTT, you look for the blue striped bars, and for the copper, you look for the solid black bars. For the AA, you look for the solid black bars. It's a bit of a complicated figure, but basically they found very similar results to our field results. So in conclusion, there are lots of ROS assays and lots of conditions, and the results do depend rather strongly on the extraction solution and the assay. I didn't really talk about relationships with quinones in the field data. We were not really able to establish relationships with the quinones, although this may be partly due to limited amounts of quinone data and the sort of inherent scatter associated with field measurements. DTT and OH are generally well correlated with aerosol mass, but clearly mass doesn't consume DTT or generate OH. DTT and OH in the field measurements are best predicted by iron and copper, and where present, biomass burning aerosol. In most cases, iron with the ferrozene assay is much more strongly predictive than iron measured by ICP. Organics and aerosols play a significant role in adjusting the redox activity of transition metals, and this is clearly seen through the hydrogen peroxide data. DTT consumption had the same mass response in both cities, but OH did not. Fresno samples had lower and actually really remarkably low OH production, but much higher levels of hydrogen peroxide, pointing to a different distribution of reactive oxygen species. And so we have DTT that's measuring one set of things that we don't understand as well as OH and hydrogen peroxide, but the fact that the DTT is giving pretty even responses may be related to basically the distribution of ROS, which is clearly different between hydrogen peroxide and OH. And some major unanswered questions. What the assays are measuring. The chemistry is certainly complicated, but it is not intractable. Which assay is best in terms of being health predictive? That's something that we weren't really able to address with this study, but that is still a major unanswered question. The role of endogenous versus exogenous ROS, also well beyond the reach of the study, but a really important and interesting question. And the source and distribution of active iron. There are routine measurements of iron that are made, but they seem to be measuring something that is pretty unrelated to what is actually, so it's a small fraction of the iron that seems to actually be causing ROS formation together with the other components that also produce ROS. And finally, the acknowledgements. So there's a long list of people who contributed to these studies. The ones in blue are the ones who are actually out in the field making measurements and up at all hours. Michelle Kwang and Adlin Scott and David Mark Gonzalez in my group have been doing most of the data analysis and related interpretation. Kennedy Vu and James and Catalina from CSU, and of course Dr. Cherrier now here at ARB was the leader in the lab in Davis. And I'd also like to thank our hosts at Harvey Mudd College, who were particularly Professor Leela Hawkins, who was incredibly, incredibly kind and supportive of our field study there, and Mr. Proper, and our other grant manager, Dongmin Liu, who's not here. Right.
Hi. You mentioned biomass burning aerosol and then BB Hulis. Were you using those two interchangeably, or are they detected or quantified with different techniques?
So I was being a little fast and loose with the terminology, to be honest. So we collected our filters for chemical analyses, and we realized that the biomass burning was really important. So we measured them with an ethylometer. Those of you who are familiar with ethylometer measurements will realize that there are massive uncertainties in everything from the sigma factor that's assumed, the angstrom exponent, I think that our data are quite solid in terms of the relative amount to one another, but I would be reluctant to put any of those numbers on a really absolute scale. But they are optically measured and corrected for optical density on the filter and so on. And then, you pick, and you get a difference of at least a factor of 2, depending on the sigma you pick, in terms of the actual mass.
But it was all optical. It wasn't like solid phase.
No. So we're also assuming that the aerosols we have measurements at 370 and 880, so they have pretty similar ratios, angstrom exponents basically, but we're assuming that we extract a similar fraction in all the samples, but we don't have any way of measuring that.
Okay, thanks, Suzanne. I guess we have some questions from the internet for, I guess, any of you. So if you want to get up there. The first question is, will further research be conducted in the geographical areas where high concentration of quinones were detected?
I think that's for me. I think this is the plots, the geographical plots maybe generated that question. We were only measuring in one location. We were inferring where the precursors to the quinones were coming from, rather than actually measuring in those different locations. But the way things are going, it looks like the quinones maybe aren't as important as we initially thought they might be, and so it's become less of an emphasis for us. And we're focusing on other organics, although quinones is still part of the mix.
Okay, I guess you did do some back calculations. Are there any particular sources or atmospheric conditions that you think would give a higher quinone load on the PM?
So I think based on what we've done and what others have done in the past, it's PAHs that are being photochemically oxidized to form the quinones. So I think it's really a signature of PAH photochemistry.
Okay, one more question, which probably might be more core. Based on these findings, what are implications for human health?
So we were surprised when we found that copper was the dominant, appears to be the dominant redox active species in these assays. So for us, that really points to more research is needed for copper. And so as I mentioned before, OEHA, the Office of Environmental Health Hazard Assessment, is reassessing the REL. So that's essentially the allowable ambient concentration of a given toxicant. So they're reassessing the copper REL right now, and they base their studies not on acellular tests like we did, but animal tests and epidemiological tests. So it'll be very interesting to see what that data suggests a safe level of copper should be, and whether that translates then into some regulation that potentially protects health from copper.
Any sense on how far off do you think it'd be, like twofold, tenfold? I mean, I know.
Well, the current REL was based on an old single-person welder study, and the REL now is 100 micrograms per cubic meter. That's ridiculous. The PM 2.5 standard is what, 12? I can't. It's 12 micrograms per cubic meter. So, copper is not less toxic than ambient particles. So ambient levels of copper are typically a few tens of nanograms per cubic meter. And there have been some epidemiological studies, Bart Ostro at OEHA has been involved with, where they show copper lights up in some of these studies. And so we suspect that even at these low nanograms, few tens of nanograms per cubic meter, that copper may be having toxic effects.
And that REL is actually an acute REL, so normally those are pretty high. Do you think OEHA might want to look at an 8-hour or chronic REL instead?
Right, you'd think a chronic REL would probably be the most appropriate for an ambient exposure.
Okay, thanks.
Right.
And we have one question from Mike Kleiman from UC Irvine. It said, lost signal when you were going over how you did mass normaling. Can you discuss that a bit more?
Oh, sorry.
So first, hello to Mike. Second, this is a very technical question, but let me try to explain it. So there's the general mass normalization where you take your rate of loss of DTT and you just divide it by the mass concentration of PM in your extract. What we found was that the mass normalized response you get varies based on the mass that you put in the extract. And so I didn't go through the gory details, but essentially what we suggest that you do in this new atmospheric environment paper is you have to make measurements at multiple PM extract concentrations so that you can extrapolate or interpolate to a mass concentration of 10 micrograms per mil. And then you've got every sample on the same mass concentration basis in the extract, and you can actually do comparisons. And I'd be happy to talk to you about it, Mike, if you want to give me a call.
Okay, and Mike actually had another question for Suzanne. Can you describe your multivariate model with respects to the independent variables included?
I'm not entirely sure what you're getting at, Mike. Hi, Mike. But basically what we did was we took all the variables that we had and we ran them in various combinations, actually kind of from both directions, from looking at the independent variables that we would expect to produce a result and looking at just all of them together and eliminating them, and we basically came to the same final conclusion. And the results that I showed are basically the only models that had, the models that had the highest adjusted R-squared, in which all components had p-values that were below 0.5. And I think in all cases they were well below 0.5, but that was the criteria that we used.
I guess if we have no more questions for the audience, or I'd like to thank our speakers for the seminar today, as well as the audience and everyone online. Thank you.